Chapter 10.
Okay, thank you. And also, I'd like to talk about ion cyclotron waves today, and want to mention one of my co-authors, Hang Wei, just gave birth to a baby girl on Monday. So congratulations to you, Hang, if you're watching. And Bill Farrell is also one of the co-authors, but he may be asking questions because I haven't showed him the slides yet. Okay, first, our study started when we restored the Apollo surface magnetometer data, and I immediately noticed that there's a kind of interesting wave, like what is shown here. You can see that there are about several hours and very nice wave activity with frequency just below the proton gyro frequency that I could see in the Apollo data. So, and this is a time series that shows the very sinusoidal waves, and this is a very narrow band as well. So I found that was very interesting because I have been studying waves most of my time. So, and I look at locations of the moon when we saw these waves, and then I realized that the places where we can see this very nice narrow band waves are only when the moon was in the Magnetotail. So that is back here, and this is the Earth, and this is sunward. So we have a magnetosphere, and when the moon goes into the Magnetotail, the plasma environment is so different from the solar wind that it has much lower density compared with the solar wind. And the magnetic field is relatively quiet, and that's where we see these waves. And then we look at the wave frequencies compared to the proton gyro frequency and also the polarization of the waves, and we feel that these must be ion cyclotron waves. So when ion cyclotron waves means that when the ion velocity distribution is non-Maxwellian, there will be some extra energy that can resonate with the the field, so that you have this cyclotron resonance, in short. So, but I felt that people didn't report this in the past, even though there were spacecraft in the Magnetotail. So I felt that this why Apollo saw these waves must be the presence of the moon. So many spacecraft went to the Magnetotail, but they were not orbiting the moon. So I thought that the presence of the moon was critical, and so I imagined the possibilities why a moon could cause these waves, and I thought about two mechanisms. The first on the left is that when there's we have a moon, so the moon can absorb ions. So the plasma or the ion velocity distribution could be asymmetric because particles are absorbed. So you have a non-Maxwellian distribution. And second possibility is the pickup ions. Even though we have very tenuous exosphere of the moon, but it's possible, but there are pickup ions that have been observed. So if they will form distributions of ions that are pretty unstable to the generation of these type of waves. Oh, okay. So then there's a Japanese scientist, Tomoko Nakagawa, who saw our study, and she was very surprised because she has been looking at Kaguya magnetometer data a lot, but she didn't see these waves at all. So she was very surprised, and then she went back to Kaguya magnetometer data, and indeed, then she saw waves event when she looked at the data closely, and there are wave events like what I saw in Apollo data. So just I think she is putting this as in a JGR journal for review. So I'm not going to show her plots, but I summarized the conclusion, her conclusions here. That is in Kaguya data, the occurrence rate of narrowband waves is less than 1%. It's very low. It's like 0.6%. And the polarization of these waves is mostly left-handed, but there's a good portion of right-handed waves. Now, so she also looked at geotail because geotail is not orbiting the moon. She wanted to see if there's a difference. So the occurrence rate of waves is also less than 1%, but it's quite comparable. And then the waves could be seen even though the moon is not inside the magnetosphere at all. So naturally, she concluded that these waves are not associated with the moon at all, or at least statistically, there is no suggestion that these waves are associated with the moon. And also, of course, there's particle data that suggests that the waves are associated with the ions in the plasma sheet boundary layer. So then I felt, okay, now this is very interesting because first of all, I didn't feel that the occurrence rate of these waves is very that low, because this is an example when we look at Apollo surface magnetometer data, you can see, of course, this is probably one of the best cases here. You see like a wave train going through several hours, and also Apollo, not only Apollo 15, but also Apollo 16 saw basically the same event, except that the wave amplitude is smaller, and we think that is due to the conservation of pointing flux. And there's a very strong crustal field near Apollo 16 side, up to I think 300 nanotesla compared to less than 10 nanotesla at Apollo 15 side. So I went back to Apollo 15 data and look at about a year of data in the Magnetotail and see what kind of occurrence rate we get. Now, so this is the result. That is, so the horizontal axis is lunation number. So every lunation I calculate the occurrence rate of the narrowband waves. So you can see that basically several percentage points for each pass of a Magnetotail. So this is the average occurrence rate. That would be about 5%. Now, what is reported by Nakagawa using Kaguya and geotail data is down here. That's below 1%. So there is a clear difference between the two, I can see. And you can see that this sometimes it can go up to about 10%. This is actually the case I just showed you. That is when I noticed that there is such a wave in Apollo data. Okay, so Kaguya saw many other waves, like right-handed waves, and I just want to let you know that we also look at the Artemis data and saw right-handed waves there. For example, Artemis has 2 probes, and this wave, this example, the 2 probes are separated by about 6 lunar radii. You see very nice wave packets at both probes, and the polarization is right-handed clearly, but propagating roughly along field line. And people have seen this kind of wave in the past, for example, by geotail, and they have a conclusion. This is consistent with the ion beam instability. Now, but Artemis can also look at ion distribution. So top plot shows the ion energy spectrogram. So and the particles here at about a few keV is the plasma sheet particle, and we saw the wave event right over here. That's the edge of the plasma sheet. And when we look at the ion velocity distribution, of course there's a core that is roughly Maxwellian, but also there's a ion beam element in the distribution that is field earthward and field aligned. So that is consistent with the ion beam instability theory that people have talked about. However, in Apollo data, in fact, we saw a lot of events are left-handed, and this is the case when Artemis saw left-handed waves. very clearly, that is when Artemis, one of the Artemis was very close to the day side of the moon. But, see the wave packet here, and but the other probe of Artemis didn't see at all. Just one spacecraft, saw it very close to the moon, and the polarization is only slightly left-handed, not really circularly polarized, and there's a large propagation angle. I think this might be associated with an interesting ion velocity distribution that we saw. That is, there seems to be an absorption by the moon, and this event is also happening when it's not at the edge of a plasma sheet. So we think that might be consistent with the type 1 scenario that I just mentioned in the beginning. So now it seems like I haven't talked about pickup ions, and this is something that I find it very difficult to identify with the existing observations. That is, we're looking at it, the waves associated with very light ions, and these ions are hard to observe in the magnetotail because there is spacecraft potential that could expel these light ions. So, of course, the alternative explanation is that maybe pickup ions are just not important for these waves at all. So this is something that we still need to verify. So in conclusion, we find that the data from multiple sources suggests that there might be more waves that you can see on the surface of on the moon. But I feel in general that there might be several mechanisms, not only one mechanism, that can generate these waves. So still a pickup ion mechanism, that is still something that we haven't detected. But I think the best verification of ion cyclotron generation, after I go over several data sets, I feel that it would be best if we can place fields and particle instruments on the surface of the moon again. I think that would probably give us the verdict. Okay, thank you.
All right, any questions for Peter? Ian, all the way in the back. Okay. You guys should sit closer.
Yeah, just to explain the discrepancy between Kaguya and the surface measurements. How possible is it that the field, it's just the field strength? Like near surface, you expect stronger fields in general than at altitude? It's a little bit naive of a question, but
Well, I didn't mention, but what I heard from Tomoko Nakagawa is that she also looked at the wave occurrence and compare that with the crustal field distribution, and she did not see any correlation at all. So I guess, that would be the situation there. It's probably not associated with the magnetic field on the ground, but I think somehow, perhaps it's just spacecraft motion that makes it harder to see waves in space. But this is my guess only.
Hey, Peter, I found that very, very interesting, and maybe you covered this in your talk, but are you certain that you and the Kaguya observations are defining an event the same way? I mean, you have, if I'm following you, you've got two different investigators determining an event rate, and my recollection is that these are sporadic events, right? So you look at a little time period where you have a number of events occurring, and it's a matter of interpretation. Do you call that one event? Do you call that 10 events?
I try to follow. I think that's a very good question indeed. Because I think Tomoko used a criterion. I think she counts the time, the duration of the waves. I try to follow her, according to her paper. For example, the wave energy has to go over a certain level and calculate the wave interval. But I think, because there's some details that, probably won't be exactly the same, but I try to follow her criteria. Yeah.
Okay, well, yeah, I mean, you've got a factor of 10 difference in the rate, so, you know, it sounds like you've tried to make sure the
Yeah.
analysis is consistent.
Yeah.
So,
But
okay.
still, it's not the exact, identical criteria, I believe.
No, understood,
I
but
have to-
but
yeah.
if you're making an attempt to be
Yeah.
uniform, I'd be surprised that, you know, interpretation or things on the margin are gonna give you a factor of 10 difference.
Yeah, so
yeah.
my feeling is that, there, more waves are seen on the surface. That's just my
Yeah.
feeling, yeah.
That's
at this
very
point.
interesting. Thanks.
Any other questions? Okay, then I actually have one. So you showed in some of your power spectra for the waves that you can see the frequency is about half the proton cyclotron frequency. And I'm just wondering, the next heaviest ion would be helium.
Yeah.
So is there any ever evidence of something at half the helium gyro frequency? Because that would seem to me
Yeah.
to be a dead ringer for pickup ions from the
Yeah.
helium exosphere.
Yeah, I saw one case at least, I haven't gone through all the Artemis data,
Sure.
I need to confess, but I think at least one case, I think the wave frequency is exactly on the, helium plus.
Cool.
Or another event is that, it could be, I don't know if helium double plus is a possibility, or H2 plus. Sometimes we see wave frequency at those
Yeah.
levels.
Yeah. I know H2 plus has been detected by Chang'e.
Uh-huh.
He double plus not from the lunar exosphere, I
Yeah,
don't think.
but even for protons, I think, the wave growth could be at a frequency only, or maximum growth
Right.
is at a portion of the proton gyro frequency. So at this point, it's hard to distinguish for me. I mean, Bill might have a better idea, but.
Could be Doppler shifting. You can blame all those shifts by Doppler shifts.
Blame it on
Is that
Doppler
how
shift.
Doppler shift, right? This is a Doppler shift.
Okay. Right.
Cool. Okay, any other questions? Then let's thank all of our speakers again for the afternoon session.